Welcome to the first video on Chapter 6, and Chapter 6 is on right triangles. So we're going to begin with 6.1, which is on the Pythagorean theorem. So the Pythagorean theorem is very important in geometry, and what that is with any right triangle. So if you have this side is A, and this is the 90-degree angle right here. This is the hypotenuse right here because it's opposite the 90-degree angle, and this is B right here. What the Pythagorean theorem is, it's this equation right here. A squared plus B squared equals C squared. And what this means is it's the leg squared plus the other leg squared is equal to the hypotenuse. So this is very important throughout using triangles. It's only with right triangles though, so it has to have an angle of 90 degrees. And that's symbolized by this little box in the corner. And if you can find a triangle that doesn't say it has a 90-degree angle, but it does satisfy the Pythagorean theorem, then the triangle must be a right triangle. So if it fits this equation right here, then even if it doesn't say it's 90 degrees, it's a right triangle, because if it fits, only right triangles can fit the Pythagorean theorem. And now there's two other really important points of this chapter, and so the first one is that the distance of a point to a line is the length of the segment from the point to the line that's perpendicular. So if we have a line right here, and we have a point, this is the point right here. The distance from this point right here to this line is a straight line that's perpendicular to this. So this right here, from here to here, is the distance from this point to the line. It's not this is the distance or that's the distance. It's from the point perpendicular to the line, and that's how far away the point is from the line. And the second point, which you can then use this that I just showed you here, is if you have, let's say, AB, so this is A, and this is B. Point B is right there. Let's make that straight. So point B is right here, point A is right there. Okay, so if you then have a line down here, which is, let's say, C, D, imagine these are perfectly straight. If these two lines are perpendicular, so if you have AB is parallel to CD, then A and B are the same distance from line CD. So this and this, if that's straight, hang on, these two lines right there and there, these are going to be perpendicular, both of them, and they're going to be the same distance because these two lines are parallel. So that's one thing to remember, that by using the fact that the distance from a point to a line is a line that's perpendicular to that, so it's going to be the shortest distance, and so that's going to be this right here and this right here, and since they're perpendicular, they're the same distance apart the whole time, so these two lines are going to be equal, and that's another important thing to remember. And now I'm going to go over a problem to show you how the Pythagorean theorem can be used. So this is problem 6.8 in section 6.1, and so all it says is the side lengths are given here, and so they want you to find how long is CD, and they don't necessarily say this is a right angle or this is a right angle. So what you do is you think, okay, so you can just plug this in and say, okay, is AB squared plus BC squared, is it equal to AC squared? And so 9 plus 16, 3 squared plus 4 squared, that is in fact equal to 25, which is 5 squared. So we know that this is a right angle, which means this has to be at a right angle because you have 180 degrees and 90 plus 90, which is equal to 180. So now that we know this is a right angle here, we can use the Pythagorean theorem on this triangle right here. So 9 squared plus 4 squared, that's equal to CD squared. So you get 16 plus 81, which is equal to 97. So CD squared is equal to 97. And so CD is equal to square root of 97. And that's your answer right there. So that's how you can use the Pythagorean theorem, and that's just one of the many ways. This is a very important thing in triangles and right triangles, definitely. It applies to all right triangles, so you know it's going to be very important. And now I'm going to move on to section 6.2. So now I've moved on to 6.2, and 6.2 is on two special right triangles, and so it's on what essentially they just said. There's two special right triangles that you need to know. So the first I'm going to talk about looks sort of like this. So this is called the 45, 45, 90 triangle. So it's, if you see 45, 45, 90. So 45, 45, 90 is an isosceles triangle where the legs here are equal. So since it's an isosceles triangle, this is the vertex angle right there. So these two angles are equal to each other. Now, since a triangle has to be 180 degrees, and you already have 90 degrees here, these two have to add up to 90 degrees, and since they're the same, it's just 90 over 2, so this is 45 degrees, and this is 45 degrees. And that's why it's called the 45, 45, 90 triangle. Those are the angles inside of it. And so, with a 45, 45, 90 triangle, the outside lengths are x, x, and this right here, opposite the 90 degrees, is x root 2. So the x and x are the legs. So these are equal to each other, and that's why it's an isosceles triangle, because this side's equal to this side, and the base angles here are equal. So this right here is x root 2. So if the legs were 4, this would be 4, this would be 4, and this would be 4 root 2. And so that's what's important to remember about a 45, 45, 90. So if any triangle, if you don't know the insides, but it fits the pattern of x, x, and x root 2 on the biggest line, then it's a 45, 45, 90 triangle. And if it's you have two 45 degrees and a 90 right here, then it's a 45, 45, 90 triangle. So basically, it's just important to remember how this triangle is set up with x, x, and x root 2, because you're going to need to use these a lot. Now, this brings me to the next triangle, and the next triangle is called the 30, 60, 90 triangle. And again, it's named for the angles inside, so we obviously see the 90 right here. Then right here is 30, and right here is 60. Now, it's always going to look like this because if you think this 30 degrees is smaller than this 60 degrees, so this 60 degrees is going to open up to a bigger line than this 30 degrees. And when we look at the 45, 45, 90, we see x, x, and x root 2, so that's the way this is. Now for the 30, 60, 90 triangle, it's a little bit different. Right here is x, this is x root 3, and right here is 2x. And it's in the same, all 30, 60, 90 triangles are going to be like this. So if you have a triangle that fits x, x root 3, and 2x, then it's a 30, 60, 90 triangle. It has to be. And so if you have a right triangle with 30, 60, 90, then it has to fit these. And so these are the two important types of right triangles that you need to know for this chapter. Now I'm going to go over a problem that uses both of them. So I've drawn up problem 6.13 here, and it's both types of special triangles. So what they ask you to do is find all missing sides of the diagram. And so we're going to start out down here. So this right here is 60. And so because it's a 30, 60, 90 triangle, 6 here is x. So this right here has to be 6 root 3. Then it's going to be 2x, so it's going to be 12. As this is a 45, 90, this has to be a 45, so this makes a 90 triangle. So because that's the case, this side right here are the same length, which makes this side right there 12. And since this is 12 and it's a 45, 45, 90 triangle, this is x root 2, so it's going to be 12 root 2. Now, because this is 12 root 2, 12 root 2 is equal to x root 3. Then you just divide by root 3 on both sides, so root 3. So x is equal to 12 root 2 divided by root 3, which is equal to 4 root 6, because you just do, okay, times root 3 on the bottom times root 3 on the top, which ends up being 4 root 6. So you can then put 4 root 6 up here. And then you move on to say if this is x, then this is 2. So you get 8 root this length right here. And this 8 root 6 is equal to x root 2. So you just divide by root 2 and you get these sides right here, because you can tell this is a 45, 45, 90 triangle. You get that this side right here is equal to this side right here, and these two sides are going to be 8 root 3 and 8 root 3 down here. And so this is how you do problem 6.13, and that's why it's important to remember the two special right triangles. And I'm going to explain the rest of chapter 6 in another video, and I hope to see you there.